Okay, so what we're going to do now is we want to think of some of these things. We want to start figuring out. There's something called Snell's law, which I think probably most of you know from high school. I want to show you a very elegant way to get it. It's actually quite nice. So we want to talk about something called Fermat's or Fermat's principle. So with Fermat, he's French, so the T is up nose. So what is he really well known for? Fermat's.
It looks like
last theorem. Okay, what is Fermat's last theorem? Okay. We have a squared plus b squared equals c squared.
Yeah.
Okay. Can you find integers that solve this? Are there integer values of a, b, and c that solve this? Yeah. What's the famous one? 3, 4, 5, right? And let a equal 3, b equal 4, then c equals 5. Right? So I can have, 3 squared plus 4 squared equals 5 squared. Fine. Now instead, so let's say I have a to the n plus b to the n equals c to the n. Let's say the n is greater than 2. Can you have integer values that solve it? No. There are no integers that solve this. So there are no integer values. This is called Fermat's last theorem. Okay, now.
That's because
Why is it done like this? So there's a book, and basically Fermat states this, and he basically, I don't remember the exact quote. It's basically proof remarkable, but I don't have enough room to basically do the proof in this book, and then he dies. Okay, and so the question is it true or not? And people basically, it appeared to be true, and it actually was used in number theory and whatnot. And it wasn't until I want to say like 99 that was actually proved by Wiles. And basically, and it's this massive proof, and using techniques that absolutely Fermat wouldn't have access to. And so the question is, did he not have a proof? And I think most people would say he probably didn't have. I think probably most people would say that he probably thought he had a proof, but it probably wasn't correct. He just didn't realize it, but there's no way of actually knowing. But regardless, it either made him famous or infamous, depending on how you look at the fact that this theorem was not, until very, very recently proved. Yeah. In fact, if you watch the authoritative documentary called Star Trek Next Generation, according to Picard, who is a veteran of this, it realizes that it's still not solved in the 21st century. Okay, it was done before 1999 when Wiles actually did it. So, okay. Yeah. Okay, so but he did many other things as well. And one of them is going to be Fermat's principle. And what it's going to be is I'm going to tinker with this a little bit, but not really right today. Now let's say I have 2 points here. Let's say here's some initial spot, and here's some final spot. And I want to have light going from the initial spot to the final spot. So does light take this path? Does light take this path? Does it take this path here? What path does light take to go from the initial to the final spot? Okay. We're gonna do a little bit better than that. So what path?
better than straight.
I mean, we're gonna make it more profound statement. So what path does light take in traveling between the initial and final positions? So that's the question we want to ask. And Fermat's principle is going to be that basically light is going to basically going from here to here, it's going to take basically an extreme the time. So the principle states that, so Fermat's principle, it's almost always a minimum. I'm not really convinced of, I don't even know if I can make a case for some. So Fermat's principle states that light will take the path that gives an extremum in time. Okay. That makes sense. Am I still clear?
Yes, I am.
For those of you who are in classical mechanics, we're going to get a variation on this, and it's going to become basically Hamilton's least action. It's actually connected to these ideas, but we're not. It's going to be connected with the variational theory. We're not quite there yet in classical mechanics. That makes sense. So let's actually do a classic case of this. What I want to do is, let's say I have two mediums. Let's apply this. Apply this idea to light traveling between two different media. Let's actually draw this out. So I said this is going to have some index of refraction in 1, and this is going to have some index of refraction in 2. Here's basically the interface between the two. And I'm going to have light here. This is going to be the initial spot. So I'm going to say from this is going to be, I'll call this Y1. And light's going to travel here. There's some spot here. And what's going to happen here is I'm going to call this distance here X. And let's going to maybe go over here. This would be my final spot. I'll call this Y2. I'm going to say from here to here is L. Imagine this is a laser. The laser comes in here. It's going to hit, it can reflect. I'm not going to worry about the reflection yet. And then this ray going in here. This ray here that's going into the material is called the refracted ray. This is called the incident ray. The question is, what way will light go? So light wants to go from the initial spot to the final spot, such that time is extreme. Okay, what's the answer going to become? Probably most of you know this already from high school. It is
N1 sine theta 1 equals N2 sine theta 2.
exactly. That is called
Snell's law.
Snell's law. So the answer is going to be Snell's law. This is N1 sine of theta 1 equals N2 sine of theta 2. And the theta is actually measured from this line right here. This is going to be my theta 1. And this is going to be my theta 2. That's Snell's law. What I want to show you is that actually Fermat's principle gives you that result beautifully. And you will tell me how to do it. So you tell me how to do it. Yes.
So, no. I was gonna say that we can no, because there's no conservation of its intensity.
Correct. There is not.
Okay.
Okay, so we need the time to go from the initial and final spot. Tell me how to write the time it takes to go from the initial to final spot. This is going to be the time it takes
Go from
here to here,
yeah.
then plus
Well,
the time it takes to go from here to here. So your total time is equal to T1, T2. So how long is this wave in the first medium. Well. So. And so T1 is. And you mocked it, you mocked 12.
I thought it was actually the true results.
So T1 would be what? I take this distance here. I call this D1. And
Times speed.
divided by its velocity, right? We know that distance equals velocity times time if there's no acceleration. So your T is D over V. Right? So this has to be what? This has to be D1 over V1.
Yeah.
And if I call this here, then D2. This has to be plus D2 over V2.
Oh, but you can like change the D1 with something else.
I agree.
With like theta.
Well, we don't have that in there. Okay, so tell me, how can I write D1 in terms of my variable X and Y1?
X, okay, square root of X to Y1 plus
Okay, so
Square root of
X squared plus
Y1 squared.
Y1 squared, okay, over V1. Plus, I'm talking about D2 is, I want to keep that X.
Square root of X squared plus Y2 squared. Okay.
Where is this distance right here?
L minus X.
That's L minus X, right? This is L, this is X, so this is L minus X. This has to be the square root of L minus X squared plus Y2 squared over V2. Now that should be an extremum. If that's an extremum, what do we know?
Something about taking a derivative and setting it equal to 0.
If you put in the details, I agree with you. I want D total. D
V X.
X. I'm gonna be 0 for an extremum. Now, if we do this correctly, we're gonna get Snell's law. Okay. Okay, we're running out of room. I think we can squeeze that in. Okay, equals. So I'll have this 0 over. So, what is the derivative of this term here with respect to X? Close.
No, I know. Okay, it will be 2x times no. No, actually. So,
1/2.
1/2, thank you. Okay, 1/2. Right, because this is a something to 1/2 by 1/2. Parenthesis.
X squared plus Y.
X squared plus Y1 squared.
Minus 1/2
So minus 1/2 power
times 2x.
times 2x.
yeah, we're getting there.
Okay, all over the.
Your cat is open definition.
What happens over here then? Am I still, I'm still
Get the velocity.
this guy is
Well, just 2x.
plus
Oh, no. It's 2x.
1/2.
L over X squared plus.
Okay, so we get doing the we get this L minus X squared plus Y2 squared to the
Negative 1/2.
minus 1/2 power.
And then you get 2 times L
2 times L minus X
times -1.
times minus 1, good. Okay. All over my buddy V2. That makes sense? Are we happy with that? Sure. So I'll take this term here, which is negative, to the other side. I'll kill the 2's. That 2 kills that 2. That 2 kills that 2. And so what does that give me? That gives me X over 1 over V1 square root X squared plus Y1 squared equals 1 over V2. L minus X. All over square root. Of L minus X squared. Plus Y2 squared. Does this have a name? X over the sky.
Sine, cause it's.
Yeah, this is X. Here's my D1. This term here is sine theta 1. And does this have a name?
Sine theta 2.
Yeah, so you got this distance here. L minus X. For D2, this is sine theta 2. Okay, so this gives me 1 over V1, sine theta 1, equals 1 over V2, sine theta 2. Tell me how to get cells all now. What is the fundamental definition of N?
Multiplied by C on both sides.
So multiply everything through by C. This right here is N, so this is N1, sine of theta 1, N2, sine of theta 2. Make sense? Ta-da. Okay. Now you will show that, okay, the reflected ray obeys. In other words, we have our light here like this. This is our incident beam. I call this theta 1. Here's my reflected beam. Here's my refracted beam. Ooh, it's sad. I'll call this theta 2 here with this. Here's my theta reflected. Okay, what do you think you're going to show about the reflected beam? That theta reflected is going to be
Same as theta 1.
the same as theta 1. And you're going to use pretty much simple for these as well. So you're going to show that theta reflected equals theta incident. Give you another argument for this later on. So you will show theta reflected equals theta 1 equals theta incident. Okay, you're going to show that. So there's the plane that actually contains, so if you were to actually do this, the plane containing the incident, the reflected, and the refracted ray actually form a plane, and you call this the incident plane. So the incident reflected and refracted beam all lie in a plane. All the incident plane. Okay. That's your incident plane. Okay. Now, let's see the implication of this. What are the implications? Listen to this long. I owe you a lot of demonstrations. I just have to have time to set them up. I owe you a number of demonstrations. I'll set this up and you can see it. So let's see if we can move this. So let's say case one. Okay. Light traveling from a low end material to a higher end or medium. So in other words, I'm going to say N1 is going to be less than N2. Here's N1. Here's theta 1, like this. And then this is going to be theta 2. This is N2. So what's going to be the implication here? How do you think theta 2 is going to compare to theta 1?
Gonna be theta 1 is gonna be greater than theta 2.
Let's figure it out. Okay. So this is our Snell's law tells. So the question is, how does theta 2 compare to theta 1?
Wait, no, actually, so N1 sine of theta 1 equal N2 sine of theta.
Okay, so we'll start off with that N1. So theta 1 equals N2. So theta 2.
They must be equal, right? We know that N1 is greater than N2, so in order for them to be equal, theta 2 must be.
Okay, well, let's just go through it. So if we say that sine of theta 1, so this is N1 over N2.
Yeah.
Sine of theta 2. What do you know about this ratio here?
You can are both two.
Oh. Not good.
It's less than 1.
Yeah, this
No,
right here is
No, it's
this
greater
is
than 1.
right. Yes.
Is it
It has to be less than
both?
both. The sine
No,
of theta 2 is less than sine of theta 2. So therefore, theta 2 is less than theta 1. So your light is going to move toward the incident beam. This is your axis here. It's going to move actually toward. We're going to measure all the angles relative to this here. It's actually going to move toward the line here. So theta 2 moves toward the particular line. That makes sense. So you're always going to have this. This and that. Yeah, we should move toward the normal. Does that make sense? I'll give you another argument for this later on. I mean, I want a picture of it though, because it's actually kind of always a little on the tricky side to draw. Okay, what's going to be the other case?
where N1 is greater than N2.
Yeah, so let's do that one. This is case 2. And 1 is going to be greater. So what happens here? Same thing. So sine of theta 2. So what happens in this case? This is no greater than 1. So this tells me that sine of theta 2 is greater than sine of theta 1. So therefore theta 2 is greater than theta 1. So your refracted wave moves away from the normal. Refracted wave moves away from the normal. Back. Makes sense. There's some real implications here. Let's see if we now make the following. Let's take an example here. Let's say this is water. Let's say this is air. And what did I say for N? Oh, N is water. This is one of these values you want to memorize. 1.7 close 33. Okay. 1.33. Okay. N for air is effectively pretty close to 1. For those of you in the advanced lab, you're probably going to measure the index refraction for air. It's 1.0001 or something like that. It's close enough to calling it. So what do we have here? So let's say I have light that's coming here. So this right here is my theta. What's going to happen to that light when it goes out into the air? It bends away from the normal because I'm going from a high index to a low index. So it's going to go like this. Right? Here's my theta 2. It bends away. Okay. But now if I have this, I'll move my point here. Now this is my theta 1. What happens to my refracted ray?
Gonna move.
Either way.
Isn't gonna be perpendicular to the
Well, we're going to do purple.
no parallel.
So I can get another angle here like this. Extend that a little bit like this. This guy here is my new theta 2. Now I can reach an angle like this. Okay, and I call that theta critical. Or I can actually make that light ray go like that. So this right here, my theta 2 now, is 90 degrees. Okay. What angle would that be? So the angle at which that light ray, when it comes, the refracted ray is actually 90 degrees here. What would that be given by? How would you find it? Yeah, you just do Snell's law with this. Okay. So what you have here is that you have N1 sine of theta equals N2 sine of theta 2.
Wouldn't it be 90 degrees?
What? Yeah.
Yeah, because like both will be equal to 0. No.
So to have N1 sine theta critical equals N2 sine of 90 degrees. Okay, what is sine of 90 degrees? Thank you. Okay. So this is N2.
That's it.
Over N1. This is sine of theta critical. Boom. Now, what happens if I exceed the critical point?
Now it's just gonna bounce back in the water.
If I go like this, so now I have this angle here. So this is 8 theta 1 greater than theta critical. What's going to happen? It's going to entirely reflect inside here. Okay. None will get out here. And this is called total internal. What's that the basis for?
Fiber optic.
That's the whole basis for fiber optic cable. Fiber optic cable. You have your light here like this. This is your fiber. Okay. You have the light coming in like this, and it's just totally internally reflects this. Okay. That's the whole basis for fiber optic cable.
That was
The total internal reflection. It's the basis for fiber optic cable. Part of the reasons why we have a multi-billion-dollar glass corporation on the road from us is Corning is remarkably good at this. Okay, they have that. They easily have the best fiber around. There's no one who competes with the fiber. I mean, they do something to get rid of a quantum effect, and they spend billions on this. How'd you make it? You basically have a column of, you have a, what, I don't know how long the thing is, but you basically have a cylinder of glass like K bigger, so you heat it up. And then you basically pull on that bottom, and you just pull in, and it actually just pulls the fiber out. It's very thin, and then the cooling rate is something, preposterous, like 10 to the 70 Kelvin per second, the cooling rate. Something utterly preposterous.
Near that and with fire, so that's
It's very, very high.
very high.
Okay.
Intro.
Yes.
That makes sense?
Yeah.
Question for that? Now we can do something else. Okay. So you're a kid and you hop in the swimming pool. You have water up here, and you look at your legs, and what do you notice?
They're not in the right place.
They're short. It looks like you shrunk. Okay, right? Now we can understand that.
Like this one.
You're actually gonna work out this problem in the homework as well. So it's like a variation of this. So let's say here's a cup. And here's water. And here's a penny. Okay. And let's say I'm kind of looking overhead like this. And so I'm looking over the head here. Okay. Like that. Okay.
What else you just draw an eye?
There.
An eyeball.
There. Okay.
No, but. Oh,
So you're looking here, what you're going to do is you're actually going to see the image of the penny here. Okay, let's go through and figure out why. It's going to be basically this process here. So we're going to draw it like this. So when you do one of these things here like this, to get an image, you have to look at the light coming from the same spot here. So I know I get light coming from here. So what's going to happen if I have light going straight up like this from the spot here? What's going to happen? It's going to go straight up like that. Okay. So right, there's light coming from all different parts of the penny. I'm going to look at light coming from this spot here. Now let's say I have light instead going this way. Well, it's going like that. Which way would it go? All right, this is water. 1.33. This is air. 1. Which way does light go? It bends away from the normal. If you look at the light here, it's going to go off like this. Okay, now I will draw a big eyeball. So here's your big eyeball. Ooh. Like that. Okay. What does your eyeball do? Your eyeball basically extrapolates this right back here. Here. And where these two rays intersect, right? Because it's going to extrapolate this way back. And this right back here. And you're going to actually see the image formed. There. Okay, so what animals are good at this? Bear. Okay, right. So there you have water. You have fish. You have a bear. Very thin. It's hungry. Okay. And what does the bear know to do? The bear realizes is, it's going to see the image here. It's not stupid. Okay. Might be stupid. I honestly don't know. Okay, but it knows basically not to go for the image here. It knows to basically go for the fish down here. The fish is always lower. And so bears are good at this. Good to know. Okay, questions for that? There's another implication of this. Okay, any questions of this part? There's another important angle too called the Brewster's angle or the polarization angle. So another important angle is Brewster's or the polarization angle. So that's going to be this. I'll say this is N1 and this is N2. Here's my number. So I can have light going in like that. I'll call this theta polarization, theta P. Now, how's the reflected ray going to have to go? At the same angle. So this is this one here. So this right here is also in theta P. And then I'm going to have my refracted ray lines. And so here, this is my theta 2. If the polarization angle occurs when your reflected ray and your refracted ray are 90 degrees apart. Let's write that out. So, the polarization angle. Theta P. And I'll say also call Brewster's angle. Occurs when the reflected ray and the refracted ray are 90 degrees apart. Now explain what's called the polarization angle in just a minute. So first of all, let's calculate it and then let's see why it's called the polarization. Basically, this right here is going to be 100% linearly polarized. Okay, we'll see why. Okay, so let's figure out what this is. So how do I calculate that? We have N1 sine of theta 1 equals N2 sine of theta 2. Okay, N1 is at what angle? Brewster's angle, I'll call it theta B. If you ever see theta B, it's going to be Brewster's angle. Okay, so it's going to be Brewster's angle. N2 sine of theta 2. What on earth is sine of theta 2? Or what is theta 2? From that geometry, what does it have to be? What do I know about theta 2? This angle, this angle.
So theta 2. What's it?
Theta 2
Equal.
plus 90
90.
plus theta P has to be 180. Has to be 180. Right. I know that. Theta 2 plus 90 plus theta P has to equal 180. Or theta 2 plus theta P is 90. Make sense? Okay. So my theta 2 is 90 minus theta P. Let's put that in. See what we get. Am I still clear?
I think I am.
No. Now we're clear. It just doesn't mean. Okay. So there we have N1 sine theta 1 equals N2 sine 90 minus theta 1. Does sine 90 minus theta 1 have a payment?
That's fine. Let's see that one.
Exactly, right, that's the cosine. Take a sine curve, shift it by 90, you get a cosine.
Okay.
So this is n1. Sine of theta 1 equals n2. Cosine of theta 1.
So we're the attention.
Yes, we are. You take the cosine over here. Then one to the other side. This is my buddy. Ooh, my one yell at me. I changed notation on you.
It's P, it's P, it's P.
It's P. 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 Boom. So now we have another angle. Now the question is, why is this used? Why is it called the polarization angle? So if you remember when I handed out those linear polarizers, I said look at glare and trim it and see the glare go away. And I said that glare is partially linear polarized. Since glare is close to being at the Brewster's. Normally, whenever you see glare, that angle is close to Brewster's angle, so it's going to be partially linear polarized. So if you have a linear, if you have polarized sunglasses, if you turn it like this, like glare, if that glare is not going away, you're not going to polarize them. It's a very simple test.
I don't know.
There's a professor in grad school. If he was an experimentalist in solid state. If you wanted to work with him, you could. He basically had a drawer full of stuff. And he would just pull out some of the stuff and say, you know, you do like sunglasses, and here are these polarized or not. And you want to know if you knew what to do. And you'd look at glare and go like, you know, yeah, I think it is. And then he'd give you another thing, saying, how do you measure that? And he just had a whole box full of stuff, and unless you could answer that, he won't let you work with it.
That's great.
Well, I mean, there's a very famous physicist by the name of Landau. He has this thing called, there's a whole series in physics called Landau Lifshitz. Unfortunately, he was involved in a really nasty car accident. I guess he was a terrible driver. And it didn't kill him, and he wasn't a mental vegetable, but his physics ability was gone after the accident. But the people who worked with him said all you had to do is tell him basically the initial assumption you made in your theory. You'd sit down and he would drive your entire theory for you. And anyone could work with him. But he basically, the first thing was a math test. He would give you a math test, which you never got back. And he would, you know, decide whether you get the next test. And so depending on how you answered this, you could work with them or not work with them. And they're very classic texts, and you use them often in grad school. And there's a problem, and there's also a solution. So you think, wow, why would a teacher ask that? Because there's the answers there. You have to go through just as much work to get his answer, because it's a Landau answer. Which is it's just the way he worked. It's just he would just have this off one ground and say, well, clearly it's this. And there'd be a couple words explaining it, and you really had to work, but you should work with them. You have to be really good. Okay, and as a result, all the people who worked for them were just absolutely insane. Okay, what are we going with? So, polarization. So why do we call this angle the polarization angle? Okay, the reason. If the incident field, okay, is at the polarization, the reflected beam is 100% linear polarized, perpendicular to the incident plane. Let me draw and explain what that means, and I'll show you explain how that works. I actually, in grad school, one of Landau's students came. He was actually an old man. His name was Migdal. Very, very famous Russian physicist. Actually, it's Mig. He came with his son. He had a reputation for being basically having a lot of jokes and just being kind of a funny guy. And so in Landau's group, it was during the Soviet era, it was hard to get sometimes Physical Review, which is the top journal in physics. But people would get a copy of it and then would have to present it for the group that week. And there was a paper that came out that basically, when you looked at it, showed that basically quantum mechanics was fundamentally flawed. And that everything about quantum mechanics was just nonsense. And so Migdal was presenting and he gave the paper. And then I think there's this huge discussion about what was going on. It showed physics was fundamentally wrong. And then eventually Migdal went, oh, isn't this interesting about the paper? He says, let's look at the first letter of every sentence here. If you look at the first letter of every sentence here, it's spelled out like the Russian word for jackass. And then he kind of walked out of the room. And then, so he had kind of that sense of humor. Okay. But anyways, he came, he was an old man. And he gave a talk for me, and it was all, you know, the audience was bad. Probably like 400 or 600 people. And he talked for like 20 minutes or so. And then he basically says, well, now I want to talk to the graduate students, the younger physicists amongst us. And so we were all very happy because he was paying attention to us. And they proceeded to give a whole bunch of jokes. Basically, and he is actually quite a talented artist. And so there'd be things like there was a monster, and then there was like a physicist measuring the monster. And the moral of this was basically even bad theories can be quantified. Because sometimes you might make a mistake and you have to figure out why that theory doesn't work. So it can actually be quantified. And there was just a whole series of things like that. It was actually quite nice. The reason he did that, it turned out he was dying from cancer. And so this was his last thing that he could do, kind of like for some of the, just with the younger physicists in the audience. He just came across as like a sincerely nice man. His son did as well. Okay, so what do we have here? So let's say here's this angle here. This is theta p, and this is unpolarized. Incident light. So the light is traveling this way here. What does it mean to be unpolarized? So the light's coming in like this. How's the electric field going? So electric field's going like this, like this, like this. It's basically the electric field is offsetting in all directions. So, you know, the way I'll draw it is like this. And so that represents unpolarized light. What's going to happen here? This is your theta 2. This light here will be 100% linear polarized, perpendicular to the plane of the board. So how did the electric field go if it's going this way? This is going to be going in and out. So the electric field will be going in and out like that. Okay. The reason for that, we'll have to wait till 12.
Why does that need to be 100% linear polarized?
This is 100% linear polarized. There is no unpolarized like here. There's a completely linear polarized.
Oh, okay. Can you be 50% linear polarized?
But not appreciably.
Okay.
Okay. Reason tomorrow. Okay. Actually, you already know all the arguments for it. You just have to do the pieces together. Have a good day.